Thanks, Mairead. Morning, everyone. So as Mairead said, I'm Andy Lundberg. I run Passivate, an energy consultancy based in Wicklow. We mainly look at thermal bridge assessment according to Paradel requirements, but also thermal modeling for Paradel compliance overall, which is not limited to just thermal bridges. I'll go into a bit more detail on what Simon said about the definition of thermal bridging, but also look at our approach to how we actually carry out modeling, what the convention requires, what the standard requires, and also a bit of kind of my view from the coal face of doing this on a daily basis, how we work in the industry, how that might be improved, and that kind of thing. So thermal bridging, what it is, where does it occur, and how do we measure it? So by definition in the standard, a thermal bridge occurs basically, in a sense, thermal bridges are completely unavoidable. You would have to live in a sphere with no windows to say you've got no thermal bridges. And even with that, technically you have a full thermal bridge in there because the outside would be thicker than the inside. So already it's unavoidable anywhere you are. It's only a matter of to what extent they affect the heat loss or how you measure it and what effect it might have on surface condensation or mold growth in the building. So anywhere that the uniform flow of heat through the building fabric changes, you have a thermal bridge, which may or may not need to be accounted for, depending on whether you consider it to be key to the overall energy performance in the building. Simple exercise you can do, if anybody's been on the Certified Passivate Designers course or any of those talks that you might have seen around the country on envelope design, an exercise you can do to avoid thermal bridging is to look at every section and plan in your building, put a pencil anywhere you want on the thermal envelope and start running around the entire section or plan. And if you have to stop to get from one element to another element, you have a thermal bridge typically, and you should have a way of dealing with that before you proceed. So it's kind of like a game, you know, don't pass the thermal bridge until you have a solution to it. That should be an integrated approach that brings in structures, fire, acoustics, hygrothermal, vapor control, thermal continuity. So a lot of people need to be at the table to have these conversations, come up with a detailed design. It's much more complex than maybe people think, but also we lose quite a bit of time and money in this country in the way we design things and the processes we take, even though we've got this very, very demanding set of building standards, which are some of the best in Europe or the world. The processes that we go through to arrive at a design that can go to construction are not ideal. So we do lose time, money, and we make things more complex than they often need to be in overthinking and over-designing, maybe because we don't fully know how something we're doing affects somebody else who's a party to it. So that's a good exercise to go through, just to identify your thermal bridges, identify where risks may exist and how you might deal with them. You can create a full schedule of thermal bridges from doing this, and that's something Dara will talk about later on in terms of the approach to accounting for thermal bridging in a Y factor in deep, for example. So simple exercise, but can give you a lot of information. 3 different types of thermal bridges that we typically find. Constructional thermal bridges, so you might have, for example, an ORSJ, penetrating insulation at a floor level to support an OPE for a kitchen extension, whatever it might be. And what can happen is we can have lots of these different types of constructional thermal bridges happening in a building in isolated spots. There may be only 1 or 2 of them, and they can often just get ignored. As a thermal modeler, you don't go to the designer and say, these are all the things that you're going to have to assess. Typically, they'll come to you and say, here are 3 or 4 things we've found that we want you to look at, but they might not show you another 15 that you would probably say should be looked at. You just never see them until maybe too late in the day when your opinion gets asked on it, when the thing is already out of the ground, for example. So again, that goes back to process. So we typically have chi values, which are point thermal bridge values associated with those single point heat losses. Then we have repeating thermal bridges. That might be, for example, timber studs in a timber frame wall. Didn't realize there were timings on that. That's just telling me I'm talking too much about the slide. But that stuff normally gets accounted for in the U values. So timber studs or SFS studs, that kind of thing, is often included in the U value of the planar element. It's where we have geometric thermal bridges, which are due to the shape of the building. So walls have to meet roofs, roofs have to meet walls, walls have to meet windows, walls have to meet floors. All those locations constitute thermal bridges. So we have to decide whether they have to be looked at or not. And we get linear psi values for those. There's a key point on this. It all really harks back to how we carry out a deep assessment to demonstrate Paradel compliance overall. A U value, or the equations that we use to calculate U values, can only account for heat loss really in one dimension. They cannot account for two-dimensional and three-dimensional heat loss. That can only be done with finite element analysis, which is basically numerical thermal modeling. Okay. Again, you might have an SFS stud in a wall and the heat flow will change there, but in the U-value calculation, ultimately, it's actually only calculated in one dimension. An accurate calculation would be a 2D or a 3D calculation of that. We rely on U-values ultimately to calculate 80 or 90% of the fabric heat loss from the building. So we're probably missing 10, 20, maybe 30% of heat loss that can happen at thermal bridges if we don't look at it. That's the reality. So just to show you that pictorially, there are repeating thermal bridges in a flanking element, as Simon said. I think this is a laser there. Yeah. So here we have a junction. The wall flanks it, as does the roof insulated there in the ceiling plane. Same here. We have a junction between two elements, and these two elements here flank that junction. So they're called the flanking elements. Those repeating thermal bridges are included in the U-value typically, and that's all fine. That's covered in standards. Where the two elements come together, that is the linear thermal bridge that we are concerned with. There's additional heat loss happening there, most likely. That additional heat loss is happening for two reasons. One may be a lack of continuity of insulation, but the second reason for the magnitude of the thermal bridge is the way we measure our buildings in a deep assessment. So you'll often hear people talking about passive house being free of thermal bridges. It's thermal bridge free construction. It's not. It's just that the way they measure the building means that the way we account for the energy losses will result in negative psi values if you were to count them. But if you were to do a Y factor calculation on a passive house in accordance with Irish deep conventions, you'll still get a very, very good Y factor, but it will be a positive value. Okay, so you only get negative thermal bridges because in passive house we measure the building externally. And we'll talk about that now in a second, how that pictorially happens, what it means. This thermal bridge here is occurring, keep on running away from me, amazing, because we've got block work going straight through the thermal envelope. So we've got additional heat loss here, not accounted for in the U-value of that element, or this one. Now, because we have that additional path of heat flow there without a thermal break of any sort, we're going to get a dip in the surface temperature at that point there. Okay, so that may be a risk. In this situation here, we've got full continuity of insulation. So the odds on having an F4SI failure or a mold growth problem there is practically zero. You know that from modeling, you're not going to get a problem there with surface condensation. But because the arrangement of insulation around the junction, as in the change in the path of heat flow is different to what it is here and here, this constitutes a thermal bridge, and it may be key. This may be very long in the context of the building, and therefore needs to be accounted for in the Y factor overall. So it may need to be modeled anyway if it doesn't conform to the ACDs. And now we can go to that slide. So the standard that we use to calculate thermal bridges is ISO 10211. The document is generic. It's an ISO document. It's not specific to any jurisdiction. So it allows us to calculate based on the national convention, which is deep here. So we measure the building internally. On the continent, they may measure the building externally, still to the same standard. Okay. And the effect of that is very, very significant. We'll talk about it in a second. The document or the convention we use here is a BRE document called BR 497. And that describes the calculation of thermal bridges from two perspectives. One is energy. The things that affect the psi value are the junction design. So go back to that previous example. If you got a block going straight through a wall meeting a roof, for example, or you change that out for a lightweight block, that affects the junction design and affects the heat flow there and affects the psi value. Okay. But the second thing is the measurement convention. And the measurement convention actually has a bigger effect on the psi value than the design of the junction itself. You can change little bits and pieces about a block or a thermal break or insulation thickness at a wall plate or whatever it might be, and that'll change the psi value somewhat. But if you go from measuring internally to externally, that will change the psi value from possibly a positive to a negative, but it will affect it very, very greatly. So the measurement convention is important. That comes into things more so in apartments than it does in housing. But when it comes to stuff like duplexes, where you've got two separate dwellings above and below, or party walls and plan on terrace and semi-detached buildings, it actually has a significant effect. The measurement convention that we reference in deep is ISO 13789. This is a bit of a snapshot of the picture of how it tells you to measure buildings. You know, that's basically as good as it gets until you get into your BE or assessor training course, where you might get a bit more information. But one of these shows us how we measure things here in Ireland, and I've no idea which one it is, to be honest. I know how to do it right according with deep, but that's where that all comes from. So as the starting point goes for how to measure buildings, the standards aren't great, you know. So what's the difference in internal versus external dimensioning of a building? So we know our U values. We can calculate U values. We're pretty good at it. Most of us aren't expert, but we're pretty good, or we know where to go to get one. Okay. We know how to measure the building in accordance with the DEEP methodology. We're going to stop at the finished face internally there and measure that wall out to wherever it is, the far corner, and the same with this one. Okay. So when we put this into DEEP, we've got this wall here with a certain area and a certain U value. So we know the heat loss through that wall specific to this building. And the same for this one. What we're missing is that square there. We have no information on the additional heat loss through that square. And that depends on the arrangement of studs, for example, here, or the arrangement of SFS, or it might be something very bespoke where there's actually a UC, a steel column here in the corner, and it's going to be significant thermal bridge from that. We don't know. The U value and the measurement in DEEP tells us nothing about it. The only thing that can tell you about it is a linear thermal bridge calculation. If, on the other hand, we measure the building externally, so go back to the point on passive house, we've measured that wall with the same U value, we've measured it out to that point there. Okay, so we put that entire area of wall into our area calculation in DEEP, and the same thing applies to this wall here. And now we've actually measured this corner twice. So the amount of energy we think we're losing through these two walls in our DEEP calculation, say, or in our PHEP if it's passive house, is an overestimation. Okay, that's what would happen in DEEP on an internal facing external wall corner. Okay, you're measuring that area twice. So the thermal bridge, or the psi value, is probably going to be a negative value in that case, not because it absorbs energy or something, only because you've overestimated heat loss in your one-dimensional calculation, and the two-dimensional calculation you do there brings it back to get an accurate amount. Okay, so that's the key point. It's just accountancy. It's apples and oranges of energy, you know, and where you put things. It's really all there is to it. So why is thermal modeling important? Well, two basic things. You've got heat loss, which we talked about, U values, psi values, and chi values, depending on whether it's planar on an area or linear or a point. Now, the thing about heat loss is you cannot see heat loss anywhere really except on your energy bills, you know, and on your energy bills, you can't split it out into heat loss through your roof and heat loss through your floor. It's just a gas bill. You don't know where the heat is going unless you get a thermographic assessment done or something like that. But most people aren't doing that. Whereas mold growth is something that you can smell and something that you can see, and it's completely unacceptable. So really, in terms of order of importance, you might say that it's more important to carry a thermal bridge assessment to ensure you have no risk of mold, surface condensation, and interstitial condensation. And secondarily then is to look at heat loss. But as we make the requirements for Part L compliance more and more stringent in line with the EPBD, the effects of using default versus ACD versus calculated psi values becomes all the more important. And especially when it comes to multi-unit residential schemes where you've got a huge amount of repetition of detailing, the economy of scale in carrying out thermal modeling on those makes absolute sense. The savings you will make on carrying out thermal modeling to use calculated versus default values is just an absolute multiple. You know, it's a no-brainer. And that's something that QSs are probably a bit further down the road on than most other people on the design team, because they're looking at the costs, and to see an opportunity to make savings, which you can offer, they will jump on it. So a lot of stuff is often QS led because they're looking at every single penny that gets spent before it's even looked at designers, interestingly. Now, how thermal bridges are measured, a little bit on the coal face here. Step one, drawing is provided by client. Now I'm just going to stop here for a second, okay? That actually brings on PTSD for me, you know, when I say that, because it's as if you ring the client and say, oh, you want that model done, send me a drawing, and you get a perfect drawing in CAD, everything fully specified and decided. Everyone's looked at it, you know, fire, structures, acoustics, everyone's happy, just model it, it's grand. That happens in 1 out of 100 times, okay? Oftentimes, someone will say, can you carry out its thermal bridge assessments on our window details? No problem. So they send over some window details, and you look at them, and the stuff on like insulation by others, thermal break by others. And you're going, okay, what is that? And how thick is the thermal break? We don't know. And then about 2 days later, you get sent a separate package, and it's the window supplier's package. And you open them, and the window is a completely different profile to what's in the other details you got. And it's sitting on an angle that's different to the one that's in the architectural drawing that you got. And it's showing a pressed metal sill, and the other one is a concrete sill. So they're similar, but they're not the same at all, you know? So you ring your client back and say, I was looking at your details here. Which ones should we use? Like, oh, well, the window supplier will put the window in the way they're shown, but everything else in the architecture is correct. And you say, well, we need that coordinated. We need a full coordinated detail that we can work on. Okay, we get to work on that. And you say, okay, now that angle that the window is sitting on, is that designed? No. Like, okay, is that going to get designed shortly? We don't know. Just run with what we've got for now as a design intent, and we'll go with that. Okay. And there could be somebody else on the call who you can see on the camera is on another call, you know, so they're not saying anything and they're on mute. And you run through a lot of different things, thermal break thickness and what the performance might be and where the angle is going to go, and concrete versus pressed metal sill and all this kind of stuff. And everyone's happy. And then you see the engineer unmute their microphone and they say, well, you can do whatever you want there and this is all fine, but that angle is going to extend 150 mil down further than that to get a good fixing in the slab and not into the screed. But everything else is fine. And you're back to the drawing board to start again. And it goes on and on. You might say to somebody, when did you start putting these details together? And the range of answers will be anything from, well, a couple of weeks ago to, well, with COVID and all, I've had 2 kids since we started putting those details together. So that's where we're at now. You say, okay, but ultimately when you say, when are you going to site? The answer is in about 4 weeks. And what happens is about 2 or 3 years worth of design work will have gone on. You will not have been part of that as a thermal modeler. You'll get called in about 4 weeks before going to site because commencement notices are going in, etc. And a huge change to the entire design that's gone on for years will happen in this 2 or 3 week space of time. It'll probably make things more complex than they need to be. It'll introduce new costs, new procurement problems, lead times, etc. And so you kind of wonder what the previous couple of years were all about. So just a key point there on the drawing. Trying to get your hands on good quality drawings that are fully coordinated. The problem here is not our standards. The problem is the processes that we're following and how we arrive at a final detail. So we typically redraw the drawing. Go back to the start of this thing. We redraw it and construct a thermal model that's simplified but represents everything that has to go in there in accordance with the standard. We assign our boundary conditions. As Simon said earlier on, we put 20 degrees on the inside and 0 degrees on the outside. And the surface resistance values here depend on the direction of heat flow, really. We run the calculation and calculate the total amount of heat loss through that junction. And then we can use that again, accountancy wise. We can subtract from that the known heat loss from the wall, known heat loss from the roof, and we can arrive at a psi value that in this case would tell you the total heat loss from the parapet design in combination with the window head, for example, but you may be more interested in surface condensation and not split those out or whatever it might be. And then we look at surface temperatures, so the lowest temperature point occurring, and determine whether there's a risk of mold growth in that. Again, in a dwelling, that'd be okay. It's more than 15 degrees. If it's a basement in a dwelling with a swimming pool, if you're getting one of them, then it wouldn't be okay. So it very much depends on the use of the space as well. Just calling something a dwelling is not always enough. Some large complex dwellings have wellness areas and pools and that kind of thing. So you have to look at the risk in the context of the space adjacent to the junction. 3D applications that we commonly come across, and you know, back when I started doing this about 12 years ago, maybe 5 to 10% of work was in 3D modeling. Now it's probably 50% of work requires a 3D model. The requirements for 3D modeling are outlined very clearly in the standard BR 497, but it's not a perfect document. There are plenty of times when you need to carry out 3D modeling. Just know that you're correctly accounting for heat loss and not leaving something to go by the wayside. So you may, for example, have a bespoke steel structure bolted onto a concrete slab out on the building. This might be something more typical of a one-off house than multi-unit residential. We'll come back to that guy now in a second. So you need to account for that. You know, where does the heat loss from this go? It's at a junction, but it's also on the wall. Well, it needs to go somewhere. You can't just ignore it. Now, there may be a risk of internal surface condensation here if there are no thermal breaks, and this is bolted directly onto the concrete. But again, the internal insulation here will probably eliminate that risk, but if there are cold spot behind that, there are a new number of things you have to consider here. But the second thing is to identify what is the additional heat loss at this area here. Now you can either wrap that up into the linear psi value for that junction, or you can include it in the U value for the wall. There's an important thing to remember is that with U values, we do have limiting values. We've got project specific requirements and we've got limiting backstop values in parallel. So it may be the case that you're under pressure on the wall U value, so you decide to put that figure into the psi value instead because there are no upper limits on psi values, but it will affect your Y factor if you include it. Rainscreen cladding systems are becoming more and more common. we still use a lot of traditional construction, brick faced and rendered block faced, timber frame, some steel frame systems as well coming into the fold now, but a lot of them always use an outer leaf of brick or block. What we're probably going to find is that at the moment we think about design in terms of energy performance and Part L, and it's all about insulation thicknesses, thermal breaks, thermal performance, etc. We're going to have an interesting balance as we go forward and look at sustainability and embodied carbon, where things that perform well on an energy basis may be killing us on an embodied carbon perspective. And suddenly you've got a difficult decision in terms of, do we go with a rendered block, which may have a high recycled GGBS content, for example, and lower embodied carbon, or do you go with a brick, which is what the planners want, but has a much, much higher embodied carbon content. And you may find yourself having to make difficult decisions to balance carbon. So we're probably going to see more Rainscreen systems in the future, which all have these helping hand bracket systems and rails, which penetrate the insulation, and they must be accounted for. The U value calculation, this is where thermal modeling moves away from thermal bridging only. Just to get a U value on these walls often requires thermal modeling. Default, standard, and quoted chi values for the systems are often grossly underestimated. You'll commonly get U value calculations back from suppliers that will just have 2.5 stainless steel wall ties per square meter put in, no matter what the fixing system is at design. And it's funny because, well, it's not funny, it's very serious, but it's interesting that a lot of discussions will happen back and forth about insulation thicknesses required to achieve a certain U value, when no one has spotted that there's a completely incorrect accounting for fixings taking place in the U value that everyone's working off in the first place. And you have to go to what's actually being done and model that. And then you can look at insulation thicknesses required. And commonly it's the case that you reduce the insulation thickness because it's not as much as it needs to be, or it's the case that the thickness required is about 50% more than what you thought it was going to be. This would be an example of a helping hand bracket system. You might see these on some dwellings with zinc cladding or cement panels, etc. In these systems, just to go back to this for a second. Sorry, the timing should have been off on that. You'll get this bracket and model it. Now, the effect there of the fact that that rail penetrates the insulation itself when it should be further out, but you might be limited in terms of the extent of the building from a planning perspective, and the internal requirements for area mean that you're limited in your thickness available. So then you've got a rail going into the insulation. This might now be non-combustible when before it might have been a PIR. So now you're using up space. You might model the bracket with or without a thermal break and work out some values on it. The undisturbed wall value, just looking at that kind of section there, might give you a 0.118 U value. When you include the entire effect of the rail penetration and the bracket, it'll bring you up to 0.408. So you've got nearly a 4-fold increase in the U value there because of that system. Now, this is not an ideal system. It's not a great design, but it does happen. A 10 mil thermal break at the back of that plate will at least offer you some respite and get you down to 0.209. So that thermal break in that situation is doing a huge amount of work, but you're still at 0.209 when the design to that point thought you were at about 0.12. So the effect there is very serious. It's where you get very, very difficult conversations with people who have been working on something for quite a long time before you were brought on board, but no one has carried out an accurate calculation to that point. And the thing about it is, it's fully avoidable. Same thing applies to relieving angles for brickwork. These are becoming very common because they give you a nice reveal around your window and brickwork continuity without seeing fixings, etc. But what goes on behind them is quite complex and effective from a thermal performance perspective, not in a good way. But you may have, say, a balcony support angle here and a relieving angle bracket there, as well as the angle itself, penetrating the insulation in full. The work involved in working out the effect of that may mean a U value calculation on that wall and this wall, which may be a 3D calculation if it's in SFS, for example, and then a separate linear thermal bridge calculation of this junction. And only when you have that information, again, it's about subtracting your knowns from your gross unknown. Can you subtract all that away and end up with the chi value or the point thermal bridge value for those fixings, which again must be included somewhere in your overall heat loss calculations. It's unlikely that you can look at those kind of bracketry and say, that's not a key junction in my building or my Y factor calculation. So there's the example of that. A couple of key points. I'll read these out because the text is small. U values are based on planar elements or homogeneous uninterrupted insulation layers and should not be assumed early in the design phase just to achieve a compliant DPC value without some supporting evidence or experience to justify this. So If it's a case that a BER assessor runs a deep model provisionally on a design, they may hand down performance target values to the design team, might be a 0.16 U value for the wall, or whatever it might be, but there may not have been any calculations done at that point to determine whether it's even possible to achieve a 0.16 with the proposed construction system and the allowable width of the wall on that project. So it's important the second you have that done, that some provisional U value calculations are carried out. If the thermal modeler is on board, they can quickly point out that there's a fixing system here or something else that a normal U value calc won't account for, that could bring about a bit of a surprise later on down the road and should be looked at now insofar as possible. Typical adjustments to U values in accordance with the standard we work to, which is ISO 6946 and U value convention BR 443. That's some bedtime reading for you if you haven't read them yet. Will not necessarily apply, as in standard wall ties versus shelf angle brackets. You're not going to have values for shelf angle brackets in the standards that are going to be correct to your project. It's highly unlikely. For non-ACD construction using repeating, God, I can't even read that myself. For non-ACD construction using repeating brackets, assume a U value possibly to 50% higher than it is on a planar element value, so you don't get caught further down the road. And for non-standard facade systems, U value calculations provided by insulation suppliers will rarely account properly for the fixings. Okay, I won't go on that. Some key points you can read later on. DEEP has no entry point for point thermal bridges. It has linear thermal bridge entries in the form of the Y factor, which is one consolidated value, and U values. Point thermal bridges, particularly if they're repeating, must be included somewhere, either wrapped up in the U value or in a psi value, but they've got to be accounted for. They can't be ignored and they have a significant effect. Where point thermal bridges occur either at a single point or repeatedly in a planar element, they've got to be included in the U value, and that's all covered in BR 443. Where point thermal bridges occur along a linear thermal bridge, like a shelf angle bracket at a window lintel, which may be at an intermediate floor, their effects must be weighted into the linear psi value for the junction or into the U value for the wall. It depends on how you need to divide things up, but they can't be just ignored and dropped. Just talk for a second about the requirements of NSAI-accredited thermal modelers reports, and there's much more detailed information at this link here, which you'll get when you're sent out these slides after this. But the assessor must be named on the report, and they must be on the NSAI register if it's coming from the NSAI register and not an equivalent scheme. But their name must be on the report and their NSAI logo, which may do the same job. The report must list the materials, thermal conductivities, and the boundary conditions used. The report must reference the standard ISO 10211. The psi value and the FRSI value must be listed on the report. The U values assigned to the flanking elements must also be shown on the report and listed, as must the dimensions that are assigned to those in that calculation. And the BER assessor must be furnished with the report, as well as all the supporting data certs for all the materials used, as well as separate U value calculations that are fed into that. That must all be provided to the BER assessor. But I know Gary and Darrell will probably talk a bit more about requirements for BER assessors and NSAI accredited modelers a bit later on. But they're just some key points, because we do often see thermal modeling reports that have been done by external parties being sent on to us for auditing, or as work that's already been done that we therefore don't need to do. And in many, many cases, the reports are sent don't comply with the requirements of the reporting standards, as in it's impossible to interrogate it to find out if it was done properly or not. And therefore that's not a valid report. So make sure that you have all those points covered. Why use a thermal modeler? This is not me trying to sell myself at all, but just to point out how it can help the design process. You can quickly determine whether all key junctions are likely to be covered by the ACDs or whether thermal modeling is required. So there are some projects where we get the task of simply going through all the details and reviewing them and ticking off that indeed these are ACD compliant and don't need any modeling on them, and maybe identify 3 or 4 that are not in the ACDs and do require modeling. So that's one thing that is a quick and easy process to do. Provide key input to the detailed design process based on experience, and to ensure that energy losses are minimized and no surface condensation risk exists in dwellings in accordance with TGD L 2021. Value engineer details to ensure cost optimality is achieved. So we are required to carry out design and construction in a cost optimal way. That doesn't happen on a per project basis. It's basically built into the performance values that we have. But a lot of engineering of details or rationalization can happen where a huge amount of money is really being lost on thermal breaks or insulation thicknesses being implemented that really aren't needed. And the complexity of putting that together on site as well as procurement, lead times, costs, etc., can often be avoided. So that, it's often the case on multi-unit residential that thermal modeling will pay for itself over and over and over again when it comes to material savings and reductions in complexity, which lead to time and labor costs, etc. as well. And NSAI thermal modelers registers can be seen on the NSAI website, which is there. Thanks for your attention.